We're going to talk about numeration systems now. That means how do we represent with symbols the values that we use in everyday life? So we'll look at these symbols from two different perspectives. One is from an ancient perspective, and one is from the perspective of the numbers that we use. So let's start with the numbers that we use. This is what we're the most comfortable with. If I give you a bunch of smiley faces and I ask you to count how many there are, you would have no trouble telling me that there are 13 smiley faces, and you'd have no trouble writing a number that represents 13. But what's important is that inside that numeric representation, there is a place value understanding. That the 1 means there's one group of 10 smiley faces, and that the 3 means that there's 3 single smiley faces that are left over, that can't be grouped in groups of 10. So this notion of place value is really important in the numbers that we use every day. What we're going to see is that place value was not always important in numeration systems, and some civilizations used place value systems that were completely different than what we use. So let's stick with what we use so that we can get this idea of place value understood. We know that we construct numerals from 10 digits, 0 through 9. And we know that the place value for those digits that we use to construct numbers is based on powers of 10. So we have a base 10 number system. If I give you this number, we know that that's 2,867. The meaning behind each of those digits is that the 7 represents how many ones we have, or units. The 6 is how many groups of 10 we have. The 8 is how many groups of 100 we have, and the 2 is how many groups of 1,000 we have. Now, because of that, we can think of this number in expanded form as 2 times 1,000 plus 8 times 100 plus 6 times 10 plus 7 times 1. We have 2 groups of 1,000, 8 groups of 100, 6 groups of 10, and 7 groups of 1. And knowing that these powers of 10 can also be represented using exponents, we could write expanded form in another way as 2 times 10 to the third power plus 8 times 10 to the second power plus 6 times 10 to the first power plus 7 times 10 to the 0 power. Remember, anything to the 0 power is equal to the number 1. So we can take any number in our base 10 number system, and we can represent the value that is being shown by each of the separate digits and how those values combine to give us the value of the entire number. So let's take a look at Sina, who is a 7.5-year-old girl, and see how she understands place value, or in this case, really doesn't understand place value.
5, 6, 7, 8, 9. Those
Do
are
I-
the ones left over.
Do I draw a circle around those?
No. Look, you got 1, 2, 3, 4 tens, and you like put a 4 right there, and you put 4, and then you have 9 stars left over, and then you put 9 right there. 49.
Okay, so does everyone...
Children's understanding is often fragile. What they know in one setting doesn't always transfer to another.
Put the tiles so that you have groups of 10. And would you count out loud so I can hear what you're doing?
1, 2, 3, 4, 5,
And don't worry about them falling over. I just need a pile there.
7, 8, 9, 10.
You have enough to make another pile of 10? Let's see.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So how many groups of 10 do you have?
2,
And how many extra tiles do you have?
4.
Do you know how many tiles you have altogether? How would you find out?
Count.
And how would you count them?
Like 1, 2, 3.
Well, let me see you do that. Let's figure this out.
1, 2, 3.
After grouping the tiles into tens, Sina wasn't able to use this information to determine the number of tiles. She needed to count, and chose to do so one by one.
20, 21, 22, 23, 24.
You're a careful counter. Do you know how to write the number 24? Would you do that for me with this pen on the paper?
In the middle?
I'll make them big. That's great. Now, suppose I said that I didn't want 24 tiles anymore. I wanted only 16 tiles. Could you take some tiles away so you're only left with 16? How would you solve that problem?
By counting 6 back.
Okay.
1, 2, 3, 4, 5, 6.
Can you put those out away? And how many do you think are left now?
11.
You want to count and check?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18.
So you've got 18. Let's leave all these 18 a pile. And you wrote the number 24 so well. Do you know how to write 18?
I settled for 18 tiles, rather than the 16 I had asked for. Either number would allow me to further assess Sina's understanding.
Yeah, I agree. That's how you write 18. Sina, can you tell me can you show me with the tiles what 8 means?
8.
You put them right up here next to the 8.
I'm interested in Sina's interpretation of the digits in the numeral. Children often write numerals correctly, yet have no concept of place value.
So I just want to see just the 8. Kind of make it out loud.
1, 2, 3, 4, 5, 6, 7.
8. So this is just 8 tiles. When you wrote the number 18, you wrote a 1 and an 8. Can you show me what the 1 means? And when you counted 18, there were all these tiles together. So if this is the 8 and this is the 1, where do those fit? Good.
So you can see that Sina really doesn't understand what the digits of this number 18 means because she has no idea of what the importance of place value is in that number. So how do we help children understand what place value is all about? Well, there's an interesting article in the May 2011 edition of Teaching Children Mathematics that talks about how exploring ancient numbers can help students understand the place value that we use in our number system. So that's what we're going to do now. We're going to look at some ancient number systems and to see how other civilizations expressed numbers, and then we can compare that to how we express numbers. And we're going to start with the Egyptians. Here's an example of a number written on a temple in the Egyptian number system, and we're going to learn how to read a number like that. This is actually a representation of the number 1,333,331. So how did the Egyptians make their numbers? Well, it was a lot different than the way we make our numbers. It was called a modified tally system. So a tally system, basically we use symbols to count things, and there's no place value involved. The Egyptians also did not have any way to represent the number 0. They used a combination of these symbols to represent certain specific numbers, and this table is on page 166 in your book. You may want to refer to it. You can see that the vertical staff, which basically looked like our number 1, also represented their number 1. The symbol that's kind of an upside down U, a heel bone, represented the number 10 to us. Then there's a scroll that represents a 100. There is a lotus flower for 1,000, a pointing finger for 10,000, a polywog for 100,000, and then my very favorite symbol, astonished man, represents 1,000,000. So suppose we have the number 1324 to us in our Hindu Arabic number system. How do we represent that in Egyptian numerals? Well, we're going to break this apart as 1,000, so that would be one lotus flower. And then 300 would be 3 scrolls. 20 would be 2 heel bones, and 4 is 4 vertical staffs. So you can imagine with the Egyptian system, if you have a number like 9,999, it's going to take a little while to write all those symbols. So the next ancient numeration system we're going to look at is the Babylonian system. Now the Babylonians were able to write their numbers using only 2 different symbols. And here's an example of a cuneiform tablet that uses those 2 symbols to represent numbers. Now with only 2 symbols, the Babylonians had to have a place value system in order to represent numbers. And their place value system, instead of grouping by tens like our system does, grouped by 60s. They could not represent 0, and the 2 symbols that they use to represent their numbers look like these. The one is kind of a triangle that points down that represented 1, and the other one looks kind of like a less than sign, and that represented 10 to us. So let's think about this idea of place value. The Babylonians had to think about grouping by 60s. So the rightmost group represented the number of ones or units. The group to the left of that represented how many groups of 60s they have, and the group to the left of that represented how many groups of 60/60s or 3600s they would have. If they had a group to the left of that, that would represent how many 60 times 60 times 60s there are. So just like in our base 10 number system, every time you have a grouping that moves to the left, that grouping represents a place that is, in this case, 60 times greater than the one just to its right. So let's say we only have one grouping and we have these symbols in that one grouping. So we really just need to add together the values of the symbols. We have 3 tens and 2 ones, so this represents the number 32 to us. Now if we have some groups, then we have to think about the place values involved. So the place value furthest to the right is ones. The place value to the left of that is 60s. So this represents 12 60s and 23 ones, which to us is 720 plus 23, or 743. So what if we have 3 groupings? Well, remember, furthest to the right is ones. Because we're grouping by 60s, the next group to the left is how many groups of 60, and then the next group to the left is how many groups of 60/60s or 3600s we have. So we have 1 group of 3600, 11 groups of 60, and 20 ones. Now that seems a little strange to us. How could there be 20 ones? But remember, anything that is less than 60 can't be grouped as a group of 60. So any value less than 60 is going to be represented in that place that's furthest to the right. So that's 3600 plus 660 plus 20, which is 4,280. So how can we go from a number in our number system to a Babylonian number? Well, we're going to have to think about groups of 60. So if I have the number 42, there are no groups of 60 that I can make out of 42. So in terms of this place value representation, I know that we're only going to have one group of symbols. That one group of symbols has to add up to a value of 42. So 40 plus 2 is 42. So this is the number 42 in Babylonian. So what do we do with a number like 203? Well, we still have to think about this place value idea of grouping by 60s. And in 203, we do have some groups of 60. In fact, we have 3 groups of 60 with 23 left over. So we can represent the 3 groups of 60 with 3 symbols that represent 1. And then the 23 left over we represent with 2 10s and 3 1s. Now remember, there's place value involved here. So those 3 1s that you see in that group furthest to the left represent 3 60s, which is 180, plus the 23 that's represented in the group to the right. How about a number as big as 4,282? Now keep in mind the place values. We're looking for groups of 60 or groups of 3,600, and in this case we can find a group of 3,600 in 4,282. There's one group of 3,600. Now once we account for that one group of 3,600, that leaves us with 682 that we have to represent in the last 2 groups. So next we'll look at how many 60s do we have. In that 682 we have 11 60s. So we'll represent 11 in the 60s place. And then that leaves us with 22 left over. So we have 22 in the ones place. So 4,282 is one group of 3,600, 11 groups of 60, and 22 ones. Now let's look at the Mayan numeration system. Now that same Teaching Children Mathematics article that talked about using ancient numeration systems in the classroom shows a really nice activity in which students make cookies that have Mayan numerals on them, and then the activity is they have to order the numbers on the cookies from least to greatest. So we're going to learn how to read these Mayan numbers and what the place value system was for the Mayans. So the place value system for the Mayans was based on groups of 20 with one exception, which we'll talk about in just a second. The places are arranged vertically, not horizontally like we're used to. So that's a little bit different. They did have a symbol for 0, so that made them a rather advanced civilization in terms of using numbers. And the symbols that they used, you'll find on page 68 of your book, they only needed 3 symbols. The dot represented 1, the horizontal line represented 5, and then the symbol that looks kind of like a clamshell represented 0. So, how did they arrange these symbols? Well, since they arranged vertically, the grouping of symbols that is furthest on the bottom represents ones. The grouping that is just above that represents groups of 20. And here's the exception to the rule. The grouping above that does not represent groups of 2020s. It represents groups of 1820s or 360s. There's speculation about why that slight change existed for the Mayans. Some think it had to do with the calendar. They believe that the year had 360 lucky days in it. So we're not really sure why the Mayans represented their numbers this way. We just know that they did. And after that one exception, rather than doing 20 times 20, they did 2018s. Then the next grouping above that, they continued the pattern with a base 20 system. And the next group would be how many groups of 360s there are, or how many groups of 7,200s. So after that third grouping from the bottom, then they continued the place value pattern by multiplying the value by 20 each time. Let's see if we can read a Mayan number. Now it's really fairly simple. In this case we have one grouping. So we have 2 horizontal lines which represent 5s and the 4 dots which represent 1s. So we have 2 5s and 4 1s, which is 14. If we have groups of numbers, we'll have to think about the place value. So the three horizontal lines on the bottom are in the ones place. So that would be 15 ones or just 15. The next place above that is how many 20s we have. And that symbol represents 0. So we have 0 20s. And the next place above that represents, remember, not 20 times 20s, it's 20 times 18s, or 360s. So we have 2 dots, that's 2 ones, so 2 360s, which means the value to us of this number is 735. So let's try this number. There's 4 places in this number. If we start at the very bottom with the ones, there's 5 ones or 5. The next place above that is how many 20s we have. So we have a 5 and 2 ones, that's 7 20s. The next place above that is how many 360s we have, and that represents 0 360s. And then the next place above that is how many 20 times 360s we have, or 7,200s. There's 1 7,200, which means the value to us of this number is 7,345. So how do we take a number that is written in our number system and change it to Mayan? Well, we still have to think about that place value. We have to think about the fact that for the Mayans, the ones were in the bottommost place, and then the 20s, and then the 360s, and then the 7,200s. So we're going to see if we can make groups of this number out of 536. Now obviously, if we only have 536, we can't make a group of 7,200. But we could make a group of 360. There's one group of 360 in 536. We represent that 1 with a dot. Then once we've accounted for that 360, that one group of 360, that leaves us with 176 to represent in the other 2 places. So now we have to see how many groups of 20 we have in 176. Well, there's 8 groups of 20 in 176. We represent 8 with 1 horizontal line and 3 dots. So 8 20s are 160, which leaves us with 16 to represent in the final place. 16 is represented by 3 horizontal lines and 1 dot. So now we've got the number represented in Mayan. So our last numeration system is Roman numeration. And this is probably the most familiar to us in terms of the ancient numeration systems, because we do see Roman numerals. We actually do still use them. Here's an example of, at the Colosseum in Rome, the number 52 up above one of the entryways. So how did the Romans make their numbers? Well, they had what was called an additive system, which meant they took the symbols and they added their values together. They also had something called a subtractive property, which meant if they represented a smaller symbol in front of a larger symbol, that was meant to mean to subtract the smaller from the larger. And the reason they did that was that they did not allow any more than 3 of the same symbol in a row. So we're going to have to see how to deal with that and how to work with these symbols. Here's the Roman numerals. You're probably familiar with some of them. I is 1, V is 5, X is 10, L is 50, C is 100, D is 500, M is 1,000. Now they actually could represent numbers bigger than these. They would sometimes use a bar over a symbol, and if they put a bar over a symbol, that meant you were supposed to multiply that symbol by 1,000. So if they had a bar over an M, it actually meant the number 1,000,000. Now we're not going to deal with numbers that big for now, but we are going to learn how to use these symbols and the subtractive property to read Roman numerals and to write Roman numerals. Now that subtractive property can be a little tricky. Here are the smaller symbols that can be put in front of the larger symbols to represent particular numbers. For example, IV, I means 1 and V means 5. So since 1 is less than 5, that means subtract 1 from 5, which is 4. Down at the bottom, CM. C is 100, M is 1,000. So CM means subtract 100 from 1,000. So that means CM represents 900. So here's a Roman numeral. Let's see if we can read it. Sometimes it helps to kind of chunk these Roman numerals together. So for example, D means 500. CCC, that's 300s. Now X is smaller than L. 10 is smaller than 50. So we put those together, and that means 40. And I is smaller than V, so that means we're using the subtractive property. 1 from 5 is 4. So to us, this represents the number 844. So let's go back to thinking about numbers that aren't ancient numbers. And think about our base 10 number system and why we use a base 10 number system. Well, it's most likely because of this, because we happen to have two hands that each have 5 fingers on them. So when we count with our fingers. So we count 1, 2, 3, 4, 5, 6, 7, 8, 9. And think about what happens next. When we fill up both hands with fingers, that's when we have a 2-digit number, because what we're doing is grouping together those 10 ones into one group of 10. So that's how our place value system works. We're grouping by tens. If we think about smiley faces and we wanted to group in base 10, we could group 10 of the smiley faces together. And once we do that, we would have these 4 smiley faces left over, which would represent one group of 10 and 4 ones. Now think about Sina. Sina couldn't do that very well. She could certainly count groups of 10 and see that she had something left over. She had 2 groups of 10 and 4 left over, and yet she couldn't say that that was the number 24 because she didn't recognize the place value. So in our base 10 number system, we have these 10 allowable digits that we put together along with place value to represent numbers that are bigger than 9. So if we look at this number, 2,000, what is that, 24,123? Well, let's see. Let's think about the base 10 place value. So in terms of our place value, we have places that increase by a power of 10 every time we move further to the left. So when we look at this number, we can see that we have 2 groups of 10,000, 4 groups of 1,000, 1 group of 100, 2 groups of 10, and 3 ones. Remember, this is what we call expanded form. It represents the value of each of the digits in its place. So, what if we only had one hand instead of 2 hands, and we had to learn to count? Well, it's very likely we would be counting a little bit differently. We would probably still call this 1, and this 2, and this 3, and this 4, but once we got to this point, we would be filling up our hand. So what would we call that? We'd probably call it this. Now, to you, that says the number 10. In a base 5 number system, which is what we would be using if we had only one hand with 5 digits, this would not be the number 10. 10 means something very special to us in our base 10 number system. In a base 5 number system, this would represent no ones and one group of 5. So what we're going to be looking at is how we would be representing numbers if instead of using base 10, we used base 5 in this case. And we'll look at other number bases too. So a base 5 person, how would they represent this number? Now remember, if they're grouping in base 5, that means they're going to group 5 symbols together at a time. So the first thing they do is see how many groups of 5 they could make. And they could make 2 groups of 5 and then have 4 left over. So in base 5, here's how we'd write the number. Now let's talk about how we would say that number, because this can be a little confusing. To us in base 10, that looks like the number 24. But we don't want to call this 24 because saying 20 really means that we have 2 10s. And that's not what we have. We have 2 5s. So the way we're going to say this is 2 4 base 5. That means we have 2 groups of 5 and 4 1s left over. So let's talk a little bit more about what a base 5 number system would look like. It would only have 5 allowable digits, 0, 1, 2, 3, and 4. What we know of as 5 is not allowed in base 5, because as soon as we have that many of something, we would group those 5 together and call it 1, 0. If we look at this number in base 5, it means something completely different. In base 5, we would have to think about the rightmost digit still representing 1s, but the digit to the left of that represents how many groups of 5 we have. The digit to the left of that represents how many groups of 5 5s or 25s we have. The group to the left of that would represent how many groups of 5 times 5 times 5s we have, or how many 125s. The group to the left of that is how many 625s we have, and we could continue this. So remember, that's really not that much different than our base 10 number system. We group by powers of 10. This would just be grouping by powers of 5. So what would this number mean? 2, 4, 1, 2, 3 in base 5? Well, it would mean we have 2 groups of what to us are 625s, 4 groups of what to us are 125s, 1 group of what to us is 25s, 2 groups of 5, and 3 1s, which means to us this number would be 1,788 in base 10. It would still represent the same number of objects, but we just have a different name for it because we're using a base 10 number system. We're grouping by groups of 10 instead of grouping by groups of 5. Suppose we have the number 203 in base 5. Notice I did not call it 203 because that would imply we have 2 hundreds and 3 1s. That's not what we have here. This is 203 in base 5, and we want to change that to base 10. So what do those digits mean in base 5? Well, remember base 5 place value groups by 5. So that leftmost digit, that 2, represents 2 groups of 25. The middle digit, 0, means we have no groups of 5. And the rightmost digit, the 3, means we have 3 groups of 1. So to us, this would be the number 53. So 203 base 5 is the same thing as 53 in base 10. If we can talk about a base 5 number system, we can talk about any number base. So what if we have a base 4 number system? What would that look like? Well, that would mean the allowable digits we have that we can use to write numbers are 0, 1, 2, and 3. There is no 4 in a base 4 number system because once we have 4 of something, we group it together. If we look at this number in base 4, we would say 20213 base 4, and we think about what this number means. When we look at the value of the digits, we have to think about base 4 place value. Furthest to the right is the 1s. The digit to the left of that is how many groups of 4. The digit to the left of that is how many groups of 4 4s or 16s. The group to the left of that is how many groups of 4 16s or 64s. The group to the left of that is how many groups of 4 to the fourths, or 256s. And we could continue this as long as we needed to. This number is 20213 in base 4. Now what would that mean to us in our base 10 number system? Well, we have 2 groups of 256, no groups of 64, 2 groups of 16, 1 group of 4, and 3 ones, which means to us this number would represent 551. How about a base 7 number system? What would that look like? Well, it would have 7 allowable digits, 0, 1, 2, 3, 4, 5, and 6. If we wanted to take a number in base 7 and determine what it means to us in base 10, we would have to think about base 7 place value. Furthest to the right represents the number of ones. To the left of that would be how many groups of 7. To the left of that is how many groups of 7 times 7s, or 49s. To the left of that is how many groups of 7 times 7 times 7s, or 343s, and so on. Now this number is 261, which means we have 2 groups of 49, 6 groups of 7, and 1 1. So to us, this number would be 141 in our base 10 number system. So let's stretch your mind a little bit. How about a base 12 number system? Now this gets just a little bit tricky, because a base 12 number system has to have 12 digits. So we have the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but then we need a single digit to represent 10 and a single digit to represent 11. So we're going to use a T for 10 and an E for 11. So if we have the number 2TE in base 12, what does that mean to us? Well, we have to think about base 12 place value. Furthest to the right is how many ones there are in the number. To the left of that is how many groups of 12. To the left of that is how many groups of 12 squared, or 144s. And every time we have a digit that's in a place value further to the left, the value of that place increases by a factor of 12. So this number, 2TE, is telling us that we have 2 groups of 144, T meaning 10, groups of 12, and E meaning 11 ones. So to us, this number is 419. Now how do we go from numbers in our place value, base 10, to some other place value? Remember, it's all about the grouping. So if I want to take 281 and write it as a base 5 number, I have to think about that base 5 place value. Furthest to the right is the ones. To the left of that is how many groups of 5. To the left of that is how many groups of 25, and so on. And I've got to take 281 and regroup it into these groupings. Now, if I have 281, obviously I can't get any groups that are a size of 625. So I'm not going to have a 5-digit number here in base 5. But I can get some groups of 125 out of this number. I can get 2 groups of 125 out of 281. 2 groups of 125 is, well, let's see, 2 times 125 is 250. So that means out of this 281 base 10, I have taken 250 of that and grouped it into 2 groups of 125. That leaves me with 31 that I need to group by 25s. So when I look at 31, I can get 1 group of 25 out of that, which would leave me with 6 that I have left to regroup if I can. Well, in that 6, I can get 1 group of 5, which would leave me with 1 left over. So 281 base 10 is the same thing as 2111 base 5. How do I change 97 as a base 10 number into base 3? So think about base 3 place value. Base 3 place value starts with 1s to the right, groups of 3 to the left of that, groups of 3 3s to the left of that, and so on. So I'm going to think about how many of these size groups I can get out of 97, starting with whatever the largest group is I can find in 97, and that would be groups of 81. So I can get one group of 81 out of 97, which would leave me with 16 that I need to find a way to group. The next place value in my base 3 number is 27s, and there are no 27s in 16. So I look at the next place value, which is 9. There is a 9 in 16. That would leave me with 7 to represent in my number. So now I go to my next place, which is 3s. I can get 2 groups of 3 out of that 7, which would leave me with 1 left over to represent in my 1s place. So 97 as a base 10 number is the same thing as 1, 0, 1, 2, 1, base 3. Okay, and here's the challenging one. Base 12 is just going to mess with your mind a little bit. If I have 281 base 10 and I want to change it to base 12, I have to think about base 12 place value. 1 is the place furthest to the right. Then I can group 12 together at a time. Then I can group 12 12s, or 144, together. Or I can group 12 times 12 times 12 together and get groups of 1,728, which I don't have that many in this number. This is only 281. So I will not have a 3-digit number. But 281 does have some groups of 144 in it. It's got one group of 144. So if I group 144 together, that would leave me with 137 left to try to group in groups of 12. So how many 12s are in 137? Well, there's 11 12s. So 11, remember, we represent with an E. So there's 11 12s in 137. 11 12s is 132. And that leaves us with 5 left to represent in the 1s place. So 281 base 10 is the same as 1E5 base 12. So now that we've seen how to work with ancient numeration systems and how to work with some numbers in other bases, other numeric bases, we'll be moving on next time to looking at operations on numbers in base 10 and in other number bases.